So hello everyone, and welcome to the Radiation Belts in Space Physics online seminar series, which was successfully launched last month and is planned to be held at the fourth Friday every month. So my name is Wen Li from Boston University, and I'm the main organizer of today's RBSP seminar series, the topic of which is about what can we learn about energetic particle processes from laboratory experiments. So here is the entire list of our RBSP Science Organizing Committee from all over the world. And if you would like to propose any topic regarding this RBSP seminar series, please feel free to contact any of us. So it's our great honor to invite two excellent speakers, Professor Michael Mauel and Professor Jacob Bortnik, to tell us about energetic particle processes we learn from the laboratory experiments. So during their talks, please feel free to send the questions using the chat function in Zoom, and we'll try to address those questions after the talk ends. And let me first introduce our first speaker, Michael Mauel, and who is a professor at the Columbia University. So Professor Mauel builds experiments to study the plasma and explores how strong magnetic fields guide the plasma motion in the space and inside the core of the fusion energy reactors. So his current research interest includes like a nonlinear turbulent transport in magnetized plasma, energetic particle modes, as well as the relationship between the lab and the space plasma physics. So with that, let's welcome our first speaker, Professor Michael Mauel, to tell us about how lab space experiments review wave particle processes in magnetosphere. So
thank you very much. That was a wonderful introduction.
Sharing. Thank you.
And actually, for some reason I can't share. Let me try one more time. Oh, I see what I was doing. Let me try again. There it is. So thank you very much for inviting me. I was really surprised to get the invitation and really glad to be here. I will be talking about work that's been done over some time, and a lot of the work is done by my students and colleagues on various experiments, both at Columbia, MIT, and in Japan. So this idea of laboratories experiments helping space communities is probably one of the oldest in our field. And I think it's now the 125th anniversary of Birkeland's Aurora hypothesis. And for a centennial, they had this wonderful 200 kroner bill that we all have seen, a little picture of one of his largest experiments where he was beginning to understand magnetospheric currents by injecting particles into a dipolar magnetic field and looking at the glow of the plasma. On the anniversary, 100th anniversary, Chris Ripdahl and Terry Brundtland from Tromsø University wrote a sort of review of what we've learned from Birkeland's experiments. And this original experiment that you see on the bill is actually in the museum at Tromsø University. And it was really nice to see that. They wrote something that I thought was very important. And this was written in 1997. I think it's still true today. In the last decades, there seems to have been a decline of consciousness about plasma science as an independent but unifying scientific discipline. There's been a tendency towards fragmentation of plasma science into specialties like fusion plasma, space plasmas, industrial plasma processing, et cetera, et cetera. And I think what they wrote, and I agree with this, the main lesson we learned from Birkeland and other great founders of plasma science is to regain faith in the unity of basic nature of our science, to strive to tear down the walls that are erected between specialized areas. And I think that the seminar today, when we talk about laboratory experiments and space experiments, is one way in which we break down these barriers. And I'm really glad this is happening. Now, another old paper about laboratory experiments was Karl Flothhammer's review of laboratory experiments back in 1974. And he called these experiments, he classified them in two parts: scale models, or clarifying basic plasma processes. Now, I put a little X with a no on scale models. Reproduce a magnetosphere, reproduce a comet, a magnetized asteroid, the configuration, make Torella. I think that's a challenging thing to do, if not impossible, because the magnetospheric parameters are so hard to really reproduce in the laboratory. But the second part is very useful, clarifying basic plasma processes. And Falhammer wrote, magnetospheric plasma behavior is considered more complicated than simple models would predict, requiring the actual behavior of real plasmas to be determined by dedicated laboratory and theoretical investigations of basic plasma processes. And I think that's a theme, that's a modern theme of lab space exploration. Now, there are some examples of configuration investigations. There's the rather large one at the University of California, Riverside, where they built this huge machine to look at, it's called the Riverside Torella, to look at the structure of high-speed flows around a dipole field. And there's some more modern ones that's been done, and I'm showing a picture here with laser blow-off experiments, where they have a high-speed flow going around a magnetosphere to look at the structure of the bow shock. So there is some role of this, but the plasma parameters that are created in these sort of experiments are very different from what we see out in space. Now, what I'm going to talk about today is sort of more related to part two. It's an extreme example of a process experiment. And I'm actually turning the tables around, because this is how the research I'm talking about today was actually originally motivated. It wasn't so much, can I design a laboratory experiment to help answer something in the magnetosphere or about the radiation belts? It's actually the opposite. Can our observations of magnetospheric physics help us understand magnetic confinement in the laboratory? It's not what can the lab do for space physics, but what space physics can do for the lab. And that's really the subject of my talk today. This is motivated by Kira Hasegawa. Kira was invited to participate with Voyager's encounters with Uranus. And during that 12-hour flyby, he discussed the physics of magnetospheres, all the very interesting things about substorm injection, inward diffusion convection, energetic particles, radiation belts, the subject of today, centrally peak profiles, plasma moon interactions. And that motivated him to start asking the question, does magnetospheric physics apply to the magnetic confinement in the laboratory? And he was particularly interested in the inward transport of energetic particles while preserving mu and J, that's low frequency transport across magnetic field lines, that could create centrally peak pressures as observed in space, and the interchange motion of thermal plasma that preserves flux tube content and invariant temperature created, which also creates centrally peak profiles. And he asked, well, since this is often a common theme for describing magnetospheric physics, does it also work in the laboratory? So I've been involved with several experiments to begin to investigate this. It's not that these experiments were reproducing the magnetospheres, but rather they were to take basic concept of magnetospheric physics, energetic particle to confinement and transport, and see if they also apply to the laboratory. And we built some of the largest experiments ever to look at this phenomenon. Now, the magnetized confinement of plasma in things like tokamaks and stellarators and long cylinders are known for a long time. But there's something unusual with the dipole geometry that was interesting and could be investigated for the first time in these experiments. And that is, they tend to be very large with the drift frequency of the particles comparable to a megastar. Megastar is the diamagnetic drift frequency. Whereas in most laboratory plasmas, like tokamaks or long cylinders, the drift frequency is much less than the diamagnetic frequency. Now, of course, when you build something which is on the left-hand side of this, which is a dipole magnetic field with a high pressure plasma, it is different in other ways from what we see out in space. In the laboratory, we have to find a way to heat the plasma. And so we inject energy in by waves, like electron-cyclotron resonance heating. Whereas in space, a lot of the energy comes from the solar wind or the rotation of the planets, and the source of the energy is different. In some of the experiments I'm going to talk about today, there is no ionosphere, whereas magnetospheres are dominated by currents and line tying to the ionospheric regions. And then, as I'm showing on the left-hand side, there are great diagnostics. You see an array of detectors. And so the nice thing about the laboratory is you have reproducible multi-point measurements to characterize what's going on. These are the three experiments I'll talk about today. The largest ever built was at MIT. It has been disassembled for fusion experiments now. There's another one that was built in University of Tokyo and achieved the the highest pressure plasma relative to the magnetic field. And there's the original one that we built at Columbia called CTX. It's easiest to operate with lots of nice students that have been done. All of these were looking at wave particle interactions that are relevant to collisionless radial transport inside magnetospheres. We said we had many research achievements in these experiments. We had 20 PhD dissertations, 11 master's theses that spanned over 20 years. And we had lots of interesting things to talk about. I'm going to pick three. I won't do these in depth, but I want to mention these to you. The first is high plasma pressure sustained at very high plasma beta, making an artificial inflated magnetosphere, a drift resonant transport of energetic electrons by creating an artificial radiation belt, and dynamics of an internal source of particles, like an artificial moon that's evaporating inside a magnetosphere. Now, I say these things like artificial inflated magnetosphere, artificial radiation belt, and artificial moon, but I say it with a little laugh, because I'm not reproducing a magnetosphere. I'm not reproducing a radiation belt. I'm not reproducing a moon and a planet, but I'm using some of the concepts that we learned from space to see how it affects in the laboratory. We did a few other things that I'm not going to talk about. We did low frequency MHD turbulence and 2D turbulence cascades. We looked at the centrifugal instability at sonic rotation, like some of the interchange instabilities around Saturn. We did whole plasma transport modeling. We directly observed the internal turbulent pinch. We actually made an artificial ionosphere, so to speak, by controlling the currents that flow along field lines into the polar caps. And we did swarm multi-point measurements, very common theme in modern magnetospheric physics. But I'm only going to talk about the first three. So here's the first one. I'm just showing you this picture. The natural inflated high beta configuration of a planetary magnetosphere can actually be achieved in the laboratory. And I think this is remarkable. So what you see on the upper left is a picture of Jupiter with a measure of the radiation belt radiation from Cassini, reconstructed back in 2000. And it shows the magnetosphere is inflated by the pressure and the rotation in the magnetosphere. It shows the location of the radiation belts close to the planet. It shows the effect of fueling from the Io Taurus. It's a really beautiful picture that shows a lot of the phenomena inside the Jovian magnetosphere. And then down just below that is the artificial radiation belt of energetic electrons that are trapped in the MIT experiment. And then over on the right-hand side, we see pictures, reconstructions of the actual magnetic configuration in the RT1 experiment in Japan, showing how the high pressure of the plasma can inflate and extend the magnetosphere. And so this basic configuration of the magnetosphere can be reproduced in the laboratory with a lot of the MHD parameters associated with the equilibrium. Now, the next subject is talking about how we measure the global 2D plasma motion of the plasma and of radiation belts. And this research occurred over some time. It involved several different diagnostics. And I'm illustrating here in this picture the aurora. So on the bottom, we see the aurora of Jupiter. It shows the effects of the moons that are located inside of the magnetosphere. And on the top is a photograph of our auroral imager in the experiment at Columbia, where the little holes that you see are ways of detecting plasma continuously with these multi-point measurements, measuring the energy of the particles going into the auroral region. And then we can make movies and look at this as it evolves as a function of time inside the experiment. And what we're doing with this diagnostic and with related diagnostics like this is exploring the 2D plasma motion of the device. Now, our very first measurement of this involved our artificial radiation belt. And this was done, you see, in 1995. So it's been a long time. And so we produced this this artificial radiation belt by creating energetic particles that are very collisionless, trapped in a dipole magnetic field. And then we operate in such a way that they spontaneously produce pulsations that are drift resonant, where the pulsations create electric fields that rotate in the same direction as the energetic particles and lead to transport. Now, I think if I do this right, I click. Can you hear that? So this is what it sounds like. Which is really cool. It's some of the first measurements ever of drift resonant transport in the laboratory, leading to frequency chirping. Now, we learned exactly what this was about. That frequency chirping and the dynamics that you see here is only possible if we have drift resonant transport that's preserving the first and second adiabatic invariance. So it's mu-j conserving radial transport of these energetic particles. And what you're looking at here is a picture where energy is on the y-axis and time is on the x-axis. And these perturbations are creating phase space holes in this picture. And so an instability occurs and it grabs a bubble of vacuum on the outside. And this bubble of vacuum actually swirls around and propagates inward. And some plasma is moving out and some plasma is moving inward. And so each energy, whether it has a low energy at the bottom or high energy, they have slightly different drift frequencies, but they all respond with these swirling motions in phase space corresponding to the drift resonance. Using our auroral imager, we can actually measure what happens to the drift resonant energetic electrons. So here's a pulsation of these drift resonant waves. You see the electrostatic potential on the bottom. And then at the top, you see an image of just the energetic electrons that are being transported by these waves. So figure number 1 on the left-hand side is at the beginning of the pulsation. It shows the equilibrium position of the radiation belt. And then over on the right-hand side in figure 5, it shows what happens at the end of the pulsation. And what we're seeing is a direct observation of the inward transport of energetic electrons due to the drift resonant perturbations, causing the particles to move inward and also become more energetic because mu and j are conserved. Now, I would argue that this observation is really well known in the magnetospheric community for radiation belts. And what I found so significant was, and this I think is an important point, it also works in the lab. It's not like, I don't think this is telling us anything that we didn't already expect to know from the space measurements. But the fact that space measurements can help us understand what's going on in the lab is very important. Oops, let me go the other way. Now, let me just say that we learn more, and I'm just going to show this briefly. These phase space holes are at different positions in the magnetic moment or energy space. And if there's some way of popping the bubbles, filling in the holes, then we can stop the frequency chirping. And that's what we did here. We used a very small amount of chorus waves to pop the phase space bubbles that were created by this motion, and we completely suppress the frequency sweeping, indicating that the process that I was just describing of mu-j conservation breaks down if you provide something that breaks mu, and then you no longer see that phenomena. Now I'm going to switch to the third topic of the talk, which is looking at plasma turbulence spectrum and whole plasma or more thermal plasma transport. So in our experiments, we produce the energetic radiation belts most effectively when there is a low plasma density and there's a low injection of neutral gas particles in the experiment. But as we increase the gas injection, the plasma characteristics completely change. It goes from these pulsations of drift resonant instabilities resonating with the energetic electrons to a broadband turbulence of lower frequency fluctuations. And you're seeing that. So the radiation belt dynamics we occur at lower gas puff in figure A, but by increasing the fueling of the plasma, the fueling is coming from the outside to figure B, we start seeing broadband turbulence. We can understand the turbulent transport of the background plasma inside a magnetospheric geometry. The best experiment for that was the levitated dipole experiment at MIT. This is the world's largest dipole experiment. It was huge. It involved superconducting magnets. It was an amazing experiment. It worked extremely well from the first time we turned it on. We produced energetic electrons. We produced plasma transport. We looked at confinement. We had high beta plasmas. It was pretty cool. It's a magnetosphere, but it's made with a superconducting magnet, so it had no ionosphere. The magnetic field lines, when they hit the North Pole, went through the center of the magnet and came back on the South Pole. So we could make very hot plasmas where the magnetic field lines would not be touching any any object, and it means the temperature of the plasma could be very hot. So here's the scale. I'm showing you a little picture of the experiment. On the left-hand side, there's a graduate student who's inside operating equipment. And we have these detectors that look at the electrostatic fluctuations at the edge, the E cross B radial motion, the filamentary density that's coming out at the edges of the plasma. And this is sort of how we study stuff. What we're able to do is look at some time average phenomena, like the diffusion of plasma as a function of a radius. You know, how does plasma move across field lines on average? And we made those kind of measurements. Your ears are not bad. You're hearing actual plasma. So what you heard there was, without any frequency scaling, was the actual plasma turbulence. It's in an audio range. So we just stuck an antenna in a plasma and then put it to a speaker, and that's what it sounds like. What you're seeing is a whole spectrum of waves. You're looking at the spectrum here as on a log plot. There's, again, these waves are interchange-like. There's no parallel wave number. K parallel is 0, so the constant along a magnetic field line, and the frequencies that correspond to harmonics of the average drift frequency of the electrons inside. And we see a whole cascade of these. So we study these for a while, and it looks like something like this around the machine. When you actually look at the transport, you see that the edges of the plasma, the plasma has fluctuations approaching maybe a tenth of the speed of the sound. So these are very large radial pulsations coming out of the plasma, sort of filamentary things where these flux tubes are coming out, and also empty flux tubes are moving in. Now, the fueling of this plasma is on the outside, and when we made these measurements, we found the time average flux of plasma, the particles, is actually inward. So I'm showing here our expectations of what we got from simulations before we ran the experiments. The particle source is at the edge of the plasma. The center of the plasma is heated. And so what happens in a situation like this is the turbulence that we excite causes the plasma to move inward on average, and produces this situation where the number of particles in every flux tube is roughly constant, and the pressure has a sort of adiabatic profile. And we actually observed this and saw it. There's an important point in this type of experiment that I want to talk about, is this interchange mixing that occurs depends very much on a parameter called eta. Many of you know what eta is. It's a drift parameter. It's the radial variation of the temperature divided by the radial variation of the density. Now, when the eta is 2/3, if you take two flux tubes and mix them, the temperature and density profiles are completely unchanged. So eta equals 2/3 is a very magic number. It's the one of maximum entry. It's all totally mixed up. Everything's uniform. Now, when eta is bigger than 2/3, we have what's called a hot core. The temperature is hotter than the edge. And now if you mix the plasma, entropy could increase. And if eta is less than 2/3, you have a cool core. The density is peaked at the edge relative to the end. And if you mix it, you can increase entropy. But there's a magic number, which is eta equals 2/3, where you can interchange these flux tubes and nothing changes. So we wanted to measure that. So that's where our artificial moon experiment came in. When we run this experiment in the laboratory, the particle source is at the edge. But in order to get the eta parameter to change, we have to make the particle source be on the inside. So we shot an artificial moon, a lithium pellet, which about 1/3 of this evaporated as it goes through the plasma. And it provides a short period of time where the particle source is on the inside instead of the outside. And we want to see what happens. So here's I don't know if I can get this going. Yes. So here's a movie of our artificial moon shooting through the plasma. It does it in, I think it's just a few milliseconds, 17 milliseconds it goes through the plasma. And you just saw that flash, and that was the whole thing. 19 milliseconds, it's traveling at 175 meters per second, and we actually observed this, and it evaporates, filling up the center of the plasma. The peak density increases by a factor of 5. There's 3 times more electrons than there were beforehand. The energy source is from the energetic plasma, so the plasma cools as it evaporates the moon. And so you see that here. It changes for this moment. This green pulse is the lithium pulse that goes through, and that changes the profiles. The important thing is eta will change from being greater than 2/3 to being less than 2/3. And when that happens, for the first time, we see on average a planetary wind. In other words, the plasma is not that expected. There's a source of plasma on the inside, and this turbulence drives that plasma outward, and the direction of particle flux goes from being out in to being in out. And we observe the profile change. We can see what eta looks like. So as a function of time before the pellet comes in, eta is greater than 2/3. Then while the pellet's there, eta is less than 2/3. And then after the pellet, it goes back to 2/3. And we watch the density go up and how the profiles change. Now, what's really interesting about this is that this mixing changes the character of the turbulence. It reverses its direction. So on the right-hand side, you see the growth rate of the instabilities, linear growth rate that drives the turbulence, and also the frequency or the direction in which the turbulence are moving. So when eta is 2/3, it's stable. But if eta is greater than 2/3, it's unstable. When eta is less than 2/3, it's unstable. But the direction of propagation changes whether you have a cool core or a warm core. It also changes the direction of rotation and changes the particle flux. And we directly observe that in the experiments. So when eta is greater than 2/3, it moves in the electron direction. When eta is less than 2/3, it moves in the right ion direction. And we see that the direction of the particle flux changes too, which gives an idea that this concept of mixing tubes of plasma is a relatively adiabatic process. And if you mix tubes of plasma where eta is 2/3, the profiles aren't changing. But if you mix plasmas where eta is not 2/3, then you can increase the entropy by causing some instability, driving the plasma to these profiles. It's like a self-organization process. So I think my time is up. This is my main lesson learned from doing these experiments. Remember the unity and basic nature of our science, and strive to tear down the walls that are erected between specialized areas like laboratory plasma physics and space plasma physics. The question that Akira Hasegawa asked 25 years ago, does magnetospheric physics apply to the magnetic confinement in the laboratory? And the answer is yes. So we can observe some things that are happening in space and then use those things and those concepts to understand the experiments that we see in the laboratory. We've produced high pressure plasmas with an inflated magnetosphere that can be sustained continuously as long as we're heating it. That's just remarkable. The drift resonant transport of energetic electrons, our artificial radiation belt, actually preserves mu and J. It creates phase space holes which we can pop, and it causes inward transport and energization, which has been seen in space, but it also happens in the laboratory. And the dynamics of internal particle sources, like our artificial moon, changes the direction of our planetary wind from being inward to outward, and that works even in the laboratory. So I think, and then I want to thank, these these are many, but not all of the people that I worked with in these experiments from several institutions. And it's been a real pleasure to work with these people. Thank you very much.
Thank you, Mike. That was a really cool experiment and wonderful talk. Yeah, I saw a question from Dan Baker, and Dan, would you like to go ahead and speak up?
Yeah, hi, Mike, this is Dan. My question was whether the decadal survey for solar and space physics is coming up under the aegis of the National Academies. It seems like this would be a good opportunity to try to push toward the unification of the discipline of plasma physics, as you talk about. And would it be possible at all to get your sponsors, Air Force Office of Space Science Research, Space Research, and DOE, maybe to engage in that decadal survey process in some ways?
That's a really good idea, Dan. I think it'd be possible. I wouldn't mind trying to help.
Yeah.
Maybe we can talk about how I could do that. But I think that's a really good idea.
You might talk to your sponsors and tell them to talk to the Academy folks and to NASA, which will be the principal sponsor, and
I'll
see if
certainly
we
do
can
that.
push in that direction at least.
Let me just say that the sophistication of space plasma physics these days truly impresses me. It's more than just looking at phenomena. It's trying to model and understand that phenomena. And the level of diagnostics and the modeling tools that are being brought to understand our measurements in space. There's this old saying, Dan, maybe you were the one who did it. I'm not sure who said this, but our space satellites and instruments are becoming some of the best laboratories to do plasma physics. And I think it's even more important, this theme of breaking down barriers and specialization and trying to unify some of the underlying fundamental concepts is more important today than it ever has been. There's opportunities all around.
Well, your work has been terrific, and we ought to try to push in that direction. I think that'd be a terrific thing to do. Thanks.
Thank you. I believe audience will have more questions, including myself, but I prefer to leave it to the end of the seminar after Jacob's talk finished. So please feel free to continue to send the questioning through chat or raise your hand function after Jacob's talk. Okay, so let me introduce our second speaker, Jacob Bortnik, who is a professor at UCLA. So his research interests include a variety of topics, including plasma wave and radiation belt particle dynamics, using satellite data analysis and numerical modeling, laboratory plasma studies, and most recently, the application of machine learning in space weather prediction and specification. So with that, let's welcome Professor Jacob Bortnik.
Thank you very much, Wen and Sasha. Thank you for your kind invitation. And it's a pleasure to be sharing the virtual stage with Mike Mauel. I'm a big fan of the work and enjoyed the talk tremendously. So let me switch gears just a tiny bit. I'm going to be talking about understanding magnetospheric wave excitation and wave particle interactions through laboratory observations. This is possibly what Mike spoke about as what can the lab do for space physics, and Feldhammer's clarifying basic plasma processes. I really like those quotes. The focus of my talk comes from studies of the radiation belts. And so I'm picturing here in the bottom right, this is a familiar picture for many of us. If you haven't seen it before, it's a band of trapped high energy electrons, roughly an MeV, in the Earth's dipolar geomagnetic field. These particles perform three periodic motions: a gyration about the magnetic field line on the scale of kilohertz, a bounce motion up and down the field line on the scale of hertz, and a drift motion around the Earth on the scale of millihertz. And so if nothing else happened, these particles would remain trapped in the geomagnetic field forever and ever. But that is not, in fact, what we observe. We observe that, especially this outer band, this outer radiation belt, is able to disappear on a time scale of an hour or so, be rebuilt to even higher levels than it was before on the time scale of a day. It has variations ranging across all kinds of time scales, from tens of minutes up to even solar cycle periods. And so really a fascinating plasma environment. And the way that I'll be studying it or presenting today is through experiments in the large plasma device at UCLA. So there's a picture of it here at the bottom. It's truly quite a remarkable device. Mike has shown a number of such devices. I have this, I'd say, relatively modest device accessible to myself. It's at UCLA. Each of these little bands you see here, this is actually a coil, so it's a magnet, and you can control them individually, so you can shape your magnetic field as you will into any number of configurations. And the way the device works, if you've never dealt with a lab plasma, there's a column right inside here. It runs right through the middle, and every second you fill the whole device with plasma from a cathode. It kind of rises up, becomes maximally dense and hot, and decays, and you kind of do your whole entire experiment in a few milliseconds at some point in the life cycle of this plasma. You measure what you want to measure, and then you repeat the whole thing. And what we typically do, since we measure waves and particles, we have a probe, and you measure your experiment somewhere, and then you move the probe just a tiny bit, and you repeat the whole experiment over and over again. And just remarkably, the experiment is so repeatable that you can reconstruct slice planes, volumetric regions out of these thousands of separate independent experiments. It's quite amazing. I'll show some of that. I'd like to also thank Shin An, who was my graduate student and postdoc, who did a lot of the work that you'll see, and Bart van Kompernoll, who was the person operating the large plasma device. He sort of did all the hardware experiments for us. So that is my very brief introduction. And so back to the radiation belts. I mentioned that they are highly variable. How do we understand that variability? This is a standard picture that we often use. It pictures the Earth's magnetosphere viewed from above the North Pole. This is the magnetopause. And the way we understand the dynamics of energetic particles, this blue circle here is, for example, a drift path of an energetic electron. And in the course of its drift period, it encounters various waves, various plasma waves that occur naturally in the space environment. So here I'm picturing these are, I guess, ultra low frequency waves. This is probably magnetosonic wave. This is probably chorus. Magnetosonic waves, plasmaspheric hiss. And the particle experiences a little bit of scattering from each of these waves in different ways. It's the accumulated effects of all these different waves, ultra low frequency, whistle mode, chorus, hiss, magnetosonic waves, that shapes and controls how the population of energetic radiation belt particles evolves. The complicating factor is, of course, each of these waves has its own different effect in different regions of pitch angle and energy space, and they are time dependent. So in the course of a geomagnetic storms, some waves become intense in some regions, others become weaker. There's a trade-off between loss and acceleration processes. And ultimately, this is what shapes what you observe at the end of the day. In our present theory, we assume the waves are low and the wave-particle interactions are linear and uncorrelated, which leads to diffusive motion, but that's not necessarily true. So just to continue my setup, and I'll only have one or two more slides on this, this is how we understand a typical wave-particle interaction. The orange region shows a wave that is excited at the equator and propagating in the southward direction. And this squiggly curve represents the trajectory of an electron, and the electron propagates through the wave. And the effect of the wave on the electron is described by the good old Lorentz force. So here dPdt is the rate of change of momentum. Q times E plus V cross B. This is V. If you haven't recognized it, it's kind of hiding in the form of a momentum. And I've broken out my wave components explicitly into a wave magnetic field and a wave electric field. In a dipolar field, the particle would simply be seeing the background geomagnetic field, which is a function of latitude. In the presence of a wave, you have these additional components, B wave and E wave. This is, of course, a vector quantity. It has 3 components, X, Y, and Z, which you can readily rewrite into a parallel and a perpendicular component of velocity to the background magnetic field, and a phase term between the wave's magnetic field and the perpendicular velocity component of the particle, and that's called eta. And so you can see that there are a couple of components. This is the adiabatic variation, which simply depends on the gradient of the magnetic field, dB dz. This is the mirror force. This is the effect of the wave magnetic field, and the phase between the particle's gyro motion and the wave's rotation frequency, Doppler shifted to the frame of the particle, tells you whether your particle is in resonance or not. Okay, when d eta by dt is approximately 0, in other words, when the electron gyro frequency matches to the Doppler shifted wave frequency, d eta by dt is approximately 0. So eta is approximately constant, which means that the sine eta terms are approximately constant. And when you integrate these terms, the wave forces become cumulative. And so you have a permanent change in the adiabatic invariant of the particle. And this is how you get a resonant interaction. Okay, you can take this this set of equations and integrate them for a number of initial conditions. Here I'm showing 24 particles at an initial pitch angle of 70 degrees, propagating along the geomagnetic field line. This is latitude, propagating into a wave field, becoming resonant, and linearly scattering both in a positive and negative pitch angle direction. But if you turn up the amplitude, these particles change their nature. They are no longer linearly or diffusively scattering. They start to advect due to nonlinear bunching effect to lower pitch angles here quite substantially. And sometimes you get these other nonlinear effects called phase trapping. This is all great. These effects have been modeled and understood by myself, but many others before me for a number of decades. And the question is, how do you know this is really happening? What we see in the radiation belts is the product, the end product of thousands of these kinds of interactions happening over vast regions of space. And you're not seeing individual particles, you're seeing groups of particles in a telescope pointing in a particular direction. At best, you can get a pitch angle and energy distribution, but you don't get to see this. And so how do you know these kind of fundamental processes are happening, and how do they happen? And so, okay, this is my lead up. And so what we would like to do is we would like to use the incredible observability of laboratory plasmas to try and get at these microscopic wave particle interactions. And by wave particle interactions, I mean both flavors, the effects of waves on particles and the effects of particles on exciting and generating waves. And I'll show you 2 separate experiments that each deal with different aspects of the wave particle interaction. Here's an example. This is actual data. This is a Whistler wave. And this is a visualization that Bart van Kampernoll made. These are observations. This is actual time series made in the large plasma device. Each one of these points represents a probe that was here measuring a time series and then moved across and across over subsequent experimental shots, built up this huge volumetric image. And you can actually play this as a movie, and you can kind of see the wave field spinning up and propagating, and it's really fascinating what you can do. As a very quick recap, the large plasma device at UCLA, it's kind of stored in this big old warehouse down in Westwood. I believe it has its own substation because it consumes so much power. It's a national user facility. You can actually write your own proposal and do experiments on it anywhere in the United States. It's an 18-meter long cylinder with a 60-centimeter inner diameter. I mentioned that it has magnetic coils that can shape a magnetic field any way you wish. And background plasmas, we want them to be very cool. So we actually want, as low as possible, so they don't interact with our waves. We want to have a separate hot plasma particle beam. Okay, and I'll show you that in a moment. It has 450 radial ports. You can stick instruments into every little bit of your experiment and measure it not to death. Hopefully, you don't want to kill your experiment, but you can measure it a lot. And there's a wave generator. There's a little loop antenna inside the plasma that you can excite plasma waves at various frequencies. Okay, so that's how the hardware looks. The way the experimental setup looks schematically is, here's the cathode that I talked about. This fires once a second and it fills the entire chamber with plasma. We have a hot electron beam, and by hot I mean several keV. Typically we run it up to 4 kilovolts. So you have a beam of hot electrons that goes from left to right. I mentioned we have a little loop antenna, and it launches a wave going from right to left, and right inside here, the twain meet and interact with one another. And what you really want to see is how the Whistler wave has been affected by this probe, and there's another probe on the other side here that measures the electron beam and how it is affected by the wave. Okay, and then we're gonna, I'll show you just one of the scaling experiments that we've done, but that's the essential setup, okay? Okay, so question number one, what does the wave look like? Here is an actual wave measurement. So this is different planes perpendicular to the background magnetic field. We're just showing one component, B sub x, and you can see that as a function of time and space, there's a certain region that's occupied by a Whistler wave on the scale of a couple of wavelengths, and it evolves. You can't really see the rotation here. I did it in vector form, or I should say Bart did it in vector form. And you can see that it's actually rotating in a right-handed sense in a particular confined region of space. This is important because we want to shoot our beam right through this particular region where the wave is. And this is some modeling that my former postdoc Shintao has done. So you can see this is just a kind of a full wave model, and reproduces very well what you see in the device. So already we're kind of getting the sense that this plasma physics is working. It's doing what we think it should be doing. Oh, I have a movie. I can show you how this looks like. This is actual real data. We have slightly nicer looking versions. This is an earlier version, but just to give you a sense of what the wave field looks like at one particular plane, okay, built up from all these separate observations. Okay, here's the crux of the experiment. So I'm going to go through this in a bit of detail. This here in the top left, panel A, is the observed beam of hot particles. So imagine this is like a 4 keV electron beam coming at you. At the source where we fire the beam, we ramp up the voltage to 4 kilovolts, and we measure the current. So these are the actual particles flowing out of our beam source. If you're interested, let me see, lanthanum hexaboride, I believe, if that means anything to you. Okay, this is the actual current, the particles flowing out of our hot beam source, right? And what you want to do now is, beyond the wave field, you want to observe the same beam. We do paired experiments, Whistler on and Whistler off, because we want to see the difference that the Whistler makes to the beam. So these are paired experiments. We keep everything the same except Whistler is on and Whistler is off. Now the beam is fired directly down the magnetic field. All of these essentially in V parallel. And what you want to observe, okay, I'll talk about this a little bit later, about adapting your space experiments to the lab setting. You can't do everything, so you have to kind of be clever about it. So the way we decided to observe this wave particle interaction is to actually have the wave scatter the electrons out of the loss cone towards higher pitch angles. This is called the loss cone reflection effect. It has to do with the perpendicular becoming very, very small and kind of bouncing the particle out. because of the wave force. And so the red curve is what you observe. This is the probe observing the electron beam without a whistler on. Okay, as a function of time through the experiment. Notice the time scale, microseconds, right? We have like 100 microseconds that we do our experiment on in this 1 second long experimental window that we get. So we fire our beam, we observe the red curve, then we turn the whistler on, fire your beam again, and you'll see there's a little reduction here. The blue curve reduces because now we have fewer electrons reaching our probe. Okay, when do you start to see this divergence between the red and the blue curve? You start to see it at this point in time, call it, okay, so let's say at this point in time, what happens at this point in time? Remember that your beam voltage is ramping up, and at this particular point in time, your beam voltage has ramped up to the point that it's generating a particular energy of electrons that is able to resonate with a whistler wave. And this is what we're looking for. We're looking for the point of resonance. Only at this point, or so our theory says, should the electrons start to get kicked out of the last cone, and you should start to see any kind of resonant effect. So let's go through and I'll show you a couple of experimental shots. So now what we're going to do is we're going to vary the frequency of the whistler wave, and we again are going to do these paired shots, whistler on and whistler off. And you can see, so these are different experiments, 140 megahertz, 160, 180, 200. And what is the thing that you observe here? I'll give you a moment to look. What you're seeing is that the way the black and red curves separate, where the whistler on and whistler off separate, starts to occur at later and later times, right, during the voltage ramp. What does that mean? It means that over here, you see the greatest separation, the greatest number of electrons are kicked out of the loss cone at the very highest voltages that we have, okay? As you increase the frequency, you decrease the resonant energy of electrons. This is our hypothesis. Here you can see this is the separation, the beam on, whistler on versus whistler off for different frequencies. And indeed, you see that from the dark blue curve to cyan, green, gold, and red, you see the peak of this curve moving to lower and lower voltages. And if that was not clear enough, this is the resonance condition, by the way, that we are looking for. And if you plot the resonant beam voltage estimated from theory in the shaded region versus our wave frequency, you see that indeed our experimental results, the separation between whistler on and whistler off, actually do fall pretty nicely along the resonant curve. And this, to us, we considered a great success. We thought that this was actually pretty phenomenal. We really loved this part. A scaling experiment, if you increase the power that you put into the whistler wave, it should in principle kick out more electrons, and in fact, it does. The net difference between whistler on and whistler off scales very nicely with the power that you stick into your antenna. Okay, so again, we feel that it is indeed wave particle resonance that we are observing here. Let me shift gears now. I feel like I'm probably running short, very short on time. Okay, let me shift gears here and talk about growing chorus in the lab. So now we're taking our hot particle source and shifting it at an angle to the background magnetic field so that it has some free energy. And indeed, when we turn on the voltage, you see this kind of response, an excitation of plasma waves in two distinct frequencies, around 0.3 and around 0.6. And those of us who work in chorus waves will recognize this as being very similar to chorus. Okay, so we've essentially made chorus in the lab. Let me show you some results of what this wave looks like when you measure it in a plane form. Here it is. You can see that this is a great example of a plasma wave. And I'm almost done with this part. And so what we can do is we can firstly start looking at different frequencies that make up this chorus wave. And here's the cool part. You can actually do a differential measurement. You can do a reference probe at one point and a floating probe that goes around at a different part, and you can start to get a measure of your wave number K perpendicular and K parallel. You can measure this experimentally for different frequencies. So that's represented by the blue star, and compare it to your dispersion curve at different frequencies. And again, lo and behold, the experiment shows you that what you've done is you've confirmed basic plasma wave theory. But here's the coolest part that we've discovered. Because you now can get an independent measure of your wave number K perp and K parallel, and the wave frequency omega, you can start to scatter plot them against one another. So KZ is on the x-axis, omega is on the y-axis, and look at how these points arrange themselves. They arrange themselves in these diagonal lines, not accidentally. If you plot your resonance condition for different resonance harmonics, you see that the points arrange themselves along different resonance harmonics. What it tells you is different resonances between the wave and particle have all kind of worked together to generate your chorus wave. It isn't just one single resonance harmonic wave particle interaction as we typically think of it. We typically think of the first normal counter streaming wave particle interaction as generating chorus. Laboratory experiments say no, or at least almost. This is your first counter-streaming resonance, and you can see that a lot of the power lies here at the 0.3 FCE position. But indeed, as you go higher in frequency, the Landau resonance and the first anomalous cyclotron resonance, these are the guys that make up your upper band of the chorus. So a completely unexpected, delightful result. You can plot the wave normal angle too here, so it gives you a tremendous amount of insight of how the waves actually work, what the plasma actually does. It's somewhat what we expect, and it's somewhat what we don't expect. And I think that's the neatest part of this experiment. Okay, my final slide is it's maybe a little bit strange. I hope that I've convinced you that lab plasma experiments have a great deal of value to offer to our community. They form a different or complementary way to probe plasma wave excitation and scattering. We've seen scattering that corresponds to resonant interaction. We've seen emissions, in other words, chorus waves excited by these 3 to 4 keV beams, frequency-dependent structure, oblique propagation, multiple resonances, and that's what I've said here. Okay, here's the point that I kind of wanted to get real for a minute. I think we all would say, in principle, lab plasmas are wonderful. Why doesn't everybody do this? Okay, and so thank you, Mike. And so, okay, let's talk about this for a moment. And I think this goes back to Dan's point about the decadal survey. And it goes back to what is actually happening on the ground. Why don't more people do this? So I've spent a little bit of time thinking about this. Firstly, the funding to do lab space studies is meager, very, very meager. There are a very limited number of funding sources for this. And so, so this is a prime target. We have to increase the opportunities that are available to do this kind of work. Secondly, the lab equipment that I showed or Mike showed, it's pretty big, right? Not everyone can access this easily. And so we need to create opportunities, especially for students and postdocs, to be able to have some access, not only to the lab equipment, but let me tell you about this experimental insight. I mentioned in passing that we had to arrange our experiment in such a way as to shoot electrons down the field line and have them kicked out of the loss cone. We did this not coincidentally, but after, I talked to Walter Geckelman about this many times, and we tried to figure out how best to do this. Walter told me right away that what I wanted to do in a simple-minded way was impossible. Electron gyro radius was too small to do with regular lab equipment, so you had to get clever about it. And I didn't know what that meant, but luckily I had an expert who could talk to me about it. And so we need access not only to the equipment, but to insight to kind of tell you how you can actually implement some of the experiments you're thinking about. And finally, there's this disconnect that I have noticed very starkly between the space and plasma communities. Now, why does it come about? And how can you address it? Well, this kind of forum is a wonderful start. So workshops, journals that can accommodate both communities, or at least special issues or something like that, are needed, right? You need impetus for this kind of work. Secondly, I noticed that the space physics community and the lab plasma community kind of have different terms for things. They speak slightly different languages. They come from slightly different backgrounds. And so even just communicating becomes difficult. You know, we do plenty of talking, but it's the understanding that is difficult. And so we kind of had to take a little bit of effort to understand each other's language. It's not a great amount of effort, but it's non-zero either. So those are my thoughts. I hope this was helpful, interesting, stimulating, and gives us some things to do and think about. Okay, thank you.
Jacob, thank you so much for your very nice talk. Yeah, so now I'd like to open the floor to the audience for a question to either of the speakers. If you have any questions, please feel free to raise your hands up or unmute, just simply unmute yourself and speak up. Okay, then let me start with my own question then to Mike first. Yeah, so I was really impressed by the fact that the lab experiment can create artificial radiation belts through the inward radio diffusion. And as you may know, one of the hot topics in Earth radiation belt community is the relative contribution of those inward radio diffusion versus local acceleration by waves like Wizard mode waves. So I'm curious if you or your colleagues have tried to build the artificial radiation belts by launching the plasma waves like Wizard mode waves or not.
Yeah, you misunderstood a little bit about how the experiment works.
Okay, sorry.
The way the artificial radiation belt is built in the experiments I showed you is with effectively chorus waves, electron cyclotron resonance heating. So that produces, and we usually launch one frequency, so it produces a population of these quasi-relativistic particles at a location set by the frequency of the input waves. Then what we were observing is when these pulsations occur, they go further inward. So we create them at one radius. Some go out, but some go in. And so we were observing the inward transport from a location, which is at some radius, and we would see most of the energy go inward during these pulsations. We could also see the particles coming outward, some would come outward, but the pitch angle of those would not be detected by our detectors. I mean, as they go outward, because mu and J is conserved, we'd have to detect those with local gridded particle analyzers. So it was very, very interesting, but we use chorus waves or waves that we launched into plasma as a tool for manipulating the phase space density, the energy density of the electrons that are trapped in the magnetic fields. So laboratory experiments, like what Jacob said, Jacob's experiments were masterful. And they're masterful because we use the tools that we've learned and how to manipulate electrons, how to manipulate plasma, how to manipulate the pitch angle distribution by launching waves or influencing the plasma to get the plasma that we want, shooting beams in, shooting waves. So as experimentalists, we have to manipulate and change the plasma and form it to do what we want. And then we get to see phenomena. So in this case, we launch the waves that produces the artificial radiation belt. And when the density of these quasi-relativistic particles get high enough, they spontaneously make a pulsation. And this pulsation causes an inward transport that we directly observed. Now, the question, which I am very much aware of, and it's a great question, is what's the relative importance of these processes in the energization of radiation belts? And I believe they're probably both important.
Yeah, that's what we concluded from.
So as a plasma physicist, we should know that and appreciate that both of these processes are essentially important and then use them. So Jacob is using electromagnetic waves that were resonating with the particles to manipulate the phase space density. That happens naturally in the magnetosphere, but in the laboratory, it happens unnaturally using the tools that we use to manipulate the plasma.
Thank you very much. Yeah, that helps a lot. Yeah. Any other questions to either of the speakers from the audience?
I just wanted to say thank you. This is really a fantastic topic, and this was suggested in the chat, and Jacob spoke at length. This is something that we really need to talk more, especially in the context of upcoming decadal, and how to make it a more central component of the research that we do with space, and how we use leverage lab experiments to understand it.
Yeah, thank you, Sasha, for your comment. Jacob, I have one quick question for you. So from your experiment, have you seen the evidence of nonlinear interactions between visible waves and electrons?
Yeah, thanks, Wayne. That's a great question. And that's kind of where we were going. And this experiment work stopped a few years ago, unfortunately. So we never got to the nonlinear part. The nonlinear part is tricky. And, I'd have to speak to, experts like Mike and similar to really figure out how do you tease out effects like nonlinear interactions. I mean, I'm sure that if we start looking on that scale and in that level of detail, we will learn some fascinating things. I mean, this stuff just hasn't been done before. It's really hard to do, but it's doable. So yeah, I think I might have skirted your question a little bit there, but no, we haven't gotten to that point yet.
No problem. I look forward to
by the way,
studies about it.
By the way, sorry to go on, but here's an example actually of where space plasmas might actually be advantageous. The gyro radii are bigger and much more easily measurable. And so here, for example, we might use space as a natural laboratory and concoct experiments to try and see if nonlinear effects could somehow be measured, through various ways. Yeah.
Okay, thank you. Thank you very much. So I would like to thank both speakers for their wonderful talks, and thank you to the audience for attending and asking questions. And we will announce our next seminar series separately later through emails and newsletters. So have a great weekend, and see you next time, everyone.
When, thank you very much, and please put me on your mailing list.
I already did.
Okay, good, thank you.
Okay,
yes,
great.
and as Kyle mentioned, by the way, the link, we will upload this recording to the YouTube. It will be on. There's a way of fixing my mistakes, so it's all good. Thank you all.
Thank you, everyone. Have a good weekend.
You too. Thank you.
Bye.